All right, so I want to get at the question about the dipping down of the axle, and then we'll look at another property here. So one of the things about this diagram is how did the change know what direction to point in? Well, that change was caused by the gravitational torque. The gravitational torque, so if this is the bicycle wheel, I probably should demonstrate with the wheel. So as I rotate around, the direction of the gravitational torque rotates exactly the same amount. It's always going to be perpendicular to the axle, right? So what happens when the variation in a vector is always perpendicular to the vector? So let me ask, what is the time rate of change of the magnitude squared of the spin angular momentum? So that magnitude squared is the dot product between the vector L and itself. Do you agree with this step? What did I have to use? Yeah, this is, scalar products behave like normal products as far as taking derivatives are concerned. So I get 2L dotted into the derivative of L with respect to t. But that is the external torque. So the time rate of change of the angular momentum is the torque. So 2L dot tau, why is that 0? Yeah, exactly, because the angular momentum L is always perpendicular to the torque, or rather, the torque is perpendicular to the spin angular momentum. So what's constant? What's constant during the precession? Big omega. What else? L squared. By this argument, L squared. What's related to L squared? Well, yeah, magnitude of L. What else? A duck. Yeah, no. Okay, so that's constant. What else? Depends on L squared. Is that right? Kinetic energy, is that right? 1/2 I omega squared? Okay. So if I take L as I omega, then the kinetic energy would be like that. So this is a statement that if the torque is always perpendicular to the angular momentum vector, the magnitude of the angular momentum vector isn't changing, and the kinetic energy isn't changing. So this expression here says what's going to drive the precession is a torque. You take away the gravitational torque, it doesn't want to rotate around. That makes sense. It's the gravitational torque which is causing the change in the direction of the spin angular momentum. And does it make sense that the spin angular momentum should sit in the denominator? Because the bigger this L is, the longer that vector. So for the same amount of change, Okay, for the same amount of change, imagine if I put the same amount of change way out here, that's going to correspond to a smaller angle. So the rate is going to go down. So the larger the value of angular momentum of the spin, the slower the precession rate. So that means, well, let's try something. See if I can pull this off. Okay, so now I'm going to wander around a little bit and trip over these. Oh, damn. Nah, that was my fault. Okay, so can you keep it from moving? Just grab there. Okay, thanks. So as I walk around, what's happening to the direction of the gyroscope? What did you notice? So if I eliminate that torque, the gyroscope basically wants to point in the same direction. Can you imagine a use for this? So there are various animals and insects that have a version of a gyroscope. But unless there are insects in the audience, what use? Yeah, okay, it could be useful if you are in an aircraft and it's very foggy and you want to know, have you dipped down relative to the horizontal? What else? So navigation is a really big application for this gyroscopic property, that if you don't put a torque on the gyroscope, it will point in a consistent direction. So that's pretty handy, right? As we walk around on the Earth, if we had one of these things, we could just know always which direction we were in, although it would be a little cumbersome to carry around in this case.